Welcome to Tom's Maker Corner, episode 1. This is the first YouTube video I'm working on for embedded projects, or maker projects, let's call it that. And my studio is by far not ready and looks more like the desk that you see here on the picture. But hopefully still the topic to catch your interest. I'll be talking about low power microcontroller solution. I have a kind of special solution for that. My design target was to make a power control for battery applications and using also MCUs that are not so battery friendly as such. Another also very important function was to have a watchdog that is powering off the main MCU if it's not working properly. My third less important feature was to use the system as a limited non-volatile memory, and this for MCUs that do not have their own EEPROM. My first approach was to use a chip called ATtiny412. You have probably heard about this chip. It has been used quite widely. It's a 8-pin small package and can easily be put into breadboards and prototypes. For programming this, I had to make a programmer with a proper programming socket. Removing the chip from the programming was slowing down the progress and then start to be quite annoying by time. But even this was a bottleneck, but the showstopper came when the I2C didn't work properly. After a while it stopped functioning, and this was crucial as I was using it to clear the watchdog. Some YouTube creators were suggesting to look at some newer ATtiny chips called Series 1, and these have a 1-pin programming interface which is very, very handy when developing the program. My second approach was to use a chip called ATtiny412. This is a Series 1 variant of the ATtiny family. It's available only as a SMD component, but it's not too small to be soldered manually, even for myself. But I was anyhow making a PCB, so I added a ATtiny412 breakout in a corner. I also included 2 load switches, AP2141, so I could switch off the MCU and the I2C power. The breakout worked fine. Perhaps I could have added some 100k pull-ups for the enable pins, but that could be solved externally. One pin, of course, the UPDI pin, I had to reserve for flashing the chip. The breakout I made looks like this. It's just having the ATtiny itself and 2 load switches, and the rest is connectors, and here is one 3-pin UPDI programming interface, the same that is used in my programmer that I was using. To implement the software, I was planning to use the MPLAB X IDE but this failed because it didn't, at least to me, it looked like it didn't fully support the ATtiny412. So I returned back to Arduino. Putting the chip to sleep was not straightforward, but I found some very, very good hints on the internet. And in these instructions, they were not using Arduino IO functions, but rather some low-level functions that had also the advantage that they could switch off or disconnect the IO pins which was very important to reduce the power consumption. Then to the flashing and testing, I was using a small UPDI programmer that I purchased from Adafruit. It's called Adafruit High Voltage UPDI Friend, and this did the job well and worked from inside Arduino IDE quite okay. For the power consumption, I used a tool that I've been using a lot in the past, the Nordic Power Profiler Kit 2, and this is very convenient when you measure low currents and then higher currents. So the dynamic range is incredible in this profiler. Another must-have tool was the logic analyzer, and especially when you have a system where you can't reserve any pins for serial communication. This is you can't do it without a logic analyzer, I would say. I have been using the Kingst LA20716, and this has been working quite well and was very important when debugging the I2C interface. Then to the schematics. I'm not going into depth here, but just showing you what's on my application. So what we see here is an Arduino Pro Mini small module, and then a radio module called RFM69. This is a combo that I've been using in many applications and has proved to work fine. The rest here is more or less connectors and mostly used to debug the system. Then the heart of the system is the power central, could you call it. I have a voltage regulator, low quiescent voltage regulator, and then of course the ATtiny412 itself connected to the main MCU with the I2C, and then controlling a load switch that is switching on and off the power for the main MCU. Then one thing that I also wanted to have, and you need to have in a battery powered solution, is some battery level measurement, and this failed in my construction here. The issue is that this non-inverting open collector driver is leaking small currents when it's switched off, and the voltage measurement enable resistor was leaking current into the chip and caused several microamps of increased current. And even worse was in the RGB interface, because this system as such is a 3.3 volt, but I have also in most cases a bit higher voltage, perhaps even 5 volt, and this would be able to function with the RGB LEDs, but this resistor again leaked current into the open collector, so I had to remove this and not soldering this bridge here. I designed the boards with the Easy EDA tool I've been using for some time now, and it worked out well. I ordered the PCBs partly assembled from ELC PCB, and been ordering tens of PCBs lately, or different PCBs, so they have been all in kind of with high quality. This is how it looks assembled, and with the radio module that I added later, and also the Arduino Pro Mini module. Then to the test results. My application was to send one message, and what you see in this gray area is this one active time when it's sending one message over the radio interface. I have divided this most important parts into the more detailed views, A, B, and C, that we will go to next. The startup is a quite high peak, over 300 milliamps, but it's a short one, and this is not really kind of an issue here. Then the sending 63 bytes. So this is not a kind of massive data amount, but this is the maximum that the chip can send, at least the library, in one go. And this takes 3 milliseconds, and the current is over 100 milliamps during this time. But then the most important thing was that the sleep current was as low as 1.6 microamp. This is far below the target I had set to get something less than 40 microamps. So very, very happy with the results. And in sleep mode, this can run a battery a very long time. But you need, when considering the battery lifetime or runtime, you need to also estimate how often you send data. So if you send every 4 hours, then the runtime would be something like 1 year. With 24 hours, it goes something 3-4 years. These are not exact figures, but are anyhow indicative. That was all. Hope you got something out of this episode. And please give me comments, questions, and have a look in the remarks for links. Thank you.